So I think it's always valuable to kind of keep an eye on the big picture of what we're even doing, because it's really easy, especially when material gets new and crazy like this, to get lost and be like, well, what is even going on right now? I really like our textbook and the way it sets things up for us because there's going to be kind of a similar structure in our next couple chapters. To recap what's happened so far in chapter 7, the first thing in section 7.1, we learned about a new concept. It was the sampling distribution, the idea of taking repeated samples, graphing what you get, looking at that. So, sampling distribution, brand new concept, wrapping our heads around that. 7.2 is all about how that concept applies to problems with P in it. And there was all that new stuff flying at us, that large counts, that approximately normal, our new standard deviation formula, lots of crazy things to keep track of with P. In 7.3, what we're going to learn is how sampling distribution stuff applies to mu, or doing an average, instead of looking at a percent or a proportion. Now, there's a lot in like a very few amount of videos for this chapter, but the nice thing is chapter 8, 9, 10 are going to mirror this structure. Section 8.1, we're going to learn about a new concept, confidence intervals. We're going to wrap our heads around that. 8.2 is going to be, okay, how do I do that, but with P? And then 8.3 is going to be, okay, how do I do that, but with mu? And the same thing is going to happen in chapter 9 with significance tests. So you're going to become very, very comfortable with P and mu problems by the time you're done with this semester. So we've already started talking about P, and we learned that it's approximately normal, like in our Reese's Pieces machine, if certain conditions, large counts, is met. Let's talk in this lesson. We're going to get into the idea, instead of looking at a percentage, like percent orange, we're going to look at an average and look at what happens to the graph of X bar instead of P hats. And these are going to be kind of our two big things all semester long: P problems, mu problems, and learning how to deal with them. So we had, I don't know, I love this activity. So if I could, I definitely would have done this with you guys in class. We've been collecting data. I'm making this video 2020, so I don't know if we'll get to do it or not with touching a bunch of pennies and stuff like that. But I'm going to summarize the activity just to make sure. So I apologize if you already know what it is. But the idea was, I've, over the years, asked a bunch of teachers for a giant tub of pennies. It's a real big box with lots of pennies in them. And we look at what year all of those pennies are from. So we got 2020, 2019, 2018, and I don't honestly know why I start with big number on the left, but that's what I did, at least what I've done in the past. So maybe I did it reversed with you guys. And we look, and what you generally find in the population of pennies is that lots of pennies are are new. There's lots of pennies that are 2019, 2018, 2017, and so on. You don't find too many pennies from like over in the 1940s and 1950s because they've been lost or taken out of circulation. So what you end up seeing for the population of pennies is a pretty skewed graph. If you have newer pennies over here, it looks like this. If you would do it the other way, it looks more like this. But it's a skewed graph, and it goes very far. There are pennies in that box that are from 2019, 2018, stuff like that. There's the random penny in there from like 1950, 1955 as well. Lots of variability. So what we did is, over time, we took samples of pennies out of that box, and then we took an SRS of either size 5 or size 25, and we calculated the sample mean. Okay? So we found an X bar for the years on our 5 pennies. We did that for a while, got some data. Then we did the same thing, but with a sample of 25 pennies instead. And what you find, we're going to talk later about the shape in this scenario, but we found that the results were a lot more spread out for the 5 than they were for the 25. So our averages, everybody got their little X bars. There was a fair amount of spread for this one right here. People were getting averages around 2017, 2018, lots of new pennies in their sample of 5. People were getting averages in the 60s, 1960s, just lots of spread. Where in the samples of 25, they were a lot more clustered together than in the other graph. So we'll get more into the penny example next video. I just wanted to set the stage for what it was. We averaged the year of the pennies and we looked at the graph. A lot more spread here than in the 25. And that goes along with our ice cream example and everything else we've learned. Bigger samples means less variability between your samples. We'll get more on the penny thing later. There's another picture here that illustrates a pretty similar concept. This picture is looking at the population. On the left, we have the population of income for household earnings for families. And you can see right here that it's in hundreds of thousands, and this graph is my population. So what percent feel that most people are below 100,000, et cetera, et cetera. And it's income stuff is usually right skewed because most people are on the lower end, don't make as much, and then you have the people, the more you make, the less people who make that amount of money. So you will frequently see right skewed distributions when it comes to income or money in general. And then what they did is they took samples of size 100 out of that graph. So this graph on the right is when we took 100 families and we averaged their income, we got an answer, and we would put like a dots down on this graph. So that's my average from this sample of 100. Then I pick another sample of 100. Oh, I got another dot right here. Got another dot right here, here, here. There's a bunch of dots in this representing different samples of 100. Now, look at the spread on the original population from 0 to like 250-ish. Look at the spread on the sample mean graph, like 50 to 100. Much less spread. Okay, we'll get to stuff with shape later on, but what I want to point out for right now, the graph, or I'm going to say the sampling distribution of X bar is less variable, much less variable than the population. And I'll build on this observation as we go through. But this graph on the right is an X bar graph. We took averages again and again and again and again, and we graphed what we got, X bar. And we did that each single time. The graph on the left is the original population. And you can see that the X bar graph over here, I'm saying X bars graph, not bar graph. X bar is a lot less variable than your original population. In other words, if I was going to find the standard deviation of this guy, that standard deviation is going to be a lot smaller than the standard deviation for that guy. That's my first big observation I want to make right here. Okay, so let's go on to our next slide and let's learn the actual formulas here. So the mean of the sampling distribution of X bar, again, that's kind of a mouthful. It's a lot of words. In symbols, that would look like mu of X bar. So the mean of X bar's graph. It turns out, just like the mean, we learned the mean of P hat's graph was just P. The mean of X bar's graph is just the mean of your population. Okay, and you can actually see that on the previous slide right here. It marked at the bottom. There's an arrow right here for mu. Mu was like maybe 80,000 or somewhere in that range. And look at where that graph on the right peaks. It peaks right around the same spot as the actual population mean. Okay, so the average of the right graph, this guy over here, is the average for the population. They're the same. So it's an unbiased estimator, just like we talked about with P, which is good. The other thing going on is the standard deviation. And again, our book talks more about the nitty-gritty for like why it works. I'm not going to get into that too much in my videos here. But the standard deviation of the sampling distribution of X bar. So sigma of X bar, it turns out that it equals the standard deviation of the population divided by the square roots of your sample size. So it's going to be sigma over the square root of n. And it works as long as the 10% condition is met. So same thing as with P problems, you have to check the 10% condition before you're allowed to calculate your standard deviation. Two observations here. I talked on the last slide about how the standard deviation of this guy on the right is smaller than the standard deviation of this guy on the left. So if you take the formula that I have written down right here, this formula says take the standard deviation for the left guy, the population standard deviation, and divide it by something. So your answer for sigma of x bar is going to be smaller than sigma because you're always going to divide it by the square root of n. Let me show you, I didn't do it last video, I probably did in class, but just so you guys are aware, on your formula sheets, we have made it to the second page, which is exciting. And then this formula sheet is broken up into three sections, but the first two are P problems and then mu problems below that. So I've got my P stuff right here. It's just this first line. The mean of P hats graph is P. The standard deviation is that formula I taught you last time. We haven't done anything with standard error yet. That's later. And then if you scroll down to the second section for one population x bar, the mean of x bar's graph is mu, and the standard deviation for x bar's graph is sigma over root n. So our formulas are on the sheet. You do not have to memorize them, but you're going to see them enough that you'll probably inadvertently memorize them just because you use them all the time. So yeah, those are going to be our formulas. Now, we have to look at what happens to x bar's graph, because we can't just assume it's going to be normal. We have to investigate and see if that's actually the case. And with x bar, it's a tiny bit more than with P problems. We have to look at a couple things. So we're breaking this up into a couple situations. This video is going to talk about one of those situations, which is when your population is actually normal. So we're going to be looking at another internet applet here. So you guys can follow along if you want to. You don't have to. But we're looking in this video strictly at the case where the population is normal. Okay? So what does that mean? It means I'm not dealing with problems like this yet, where the population is skewed. I'm not looking at things like my penny example where my population was skewed. I'm only looking in this video at when the population is normal. Next video, we'll talk about what happens when the population is kind of funky. So in my applet here, I have a normal population. And what I'm going to do is I'm going to pick a sample of size 5. So I meant to animate that. Let me redo that here. All right. So I'm going to pick a sample of size 5 out of the population. So I'm going to pick 5 dots out of this big picture right here. So you can see, oh, I got one over there. I got 2 right here. I got 1 here. I got here. And then it graphed. It took those 5 black boxes right there and it averaged them. And it gave me an X bar right here. So if I was going to label this, and I'm not sure if I don't think my pen tool works here. This guy in blue is X bars graph. Okay. Just took a sample of size 5. I'm going to do it again. So it gives me 5 more dots. It averages those 5 dots and boom, I got a dot right there for X bar. And I do it again. Another dot for X bar. And you guys can kind of start to see what's happening right here. It's averaging the black dots and it's giving me a blue dot each time. And we're going to do that a bunch and we're going to build a little picture right here. So I'm going to do more at once. There's 5 at a time, 5 more. Again and again, you can start to see what's happening here with my picture. I'm going to do 100,000, which is just crazy. So it looks like I've done like 150,000, tons of trials right here. And you can see that X bar's graph, the blue guy, does look to be approximately normal. That was a pretty small sample size. That was size 5. Size 5 would not have flown in a P problem, not at all. But size 5 worked out for us okay right here. I'm going to change this and do a bigger example to show you that as well. But if it worked for size 5, it presumably is going to work for even bigger sizes. So I'm going to bump that up to 25 and go real big here. And if I do that, I'll show you again one animated sample. So it's pulling 25 values out of the population, 25 people. It's averaging them. And it's going to give me 1 X bar for those 25. And it's going to do it again and again and again until we build a sampling distribution. So there's 100,000, there's even more. Now this looks a little funky and it's like, oh, is that normal? It doesn't look like it's very much going on right there. It looks, I don't know, like there aren't that many choices. The scaling on this picture, I don't know how to fix that. But if you look, the scale is the same right here for all of these. If you were to zoom in on this and get a better look at it, it would be more spread out and it would look approximately normal. So what is the moral of the story for this applet right here? If the population is normal. If the population is normal, the sampling distribution of X bar's graph, will also be normal no matter what your sample size is. It worked for size 5, it worked for size 25, we don't even care. Whatever sample size you take, we're good to go, okay? Now, what we have not done yet is what if the population looked something weird like this? What if this is my population and my population isn't normal? That's going to be next video. Okay, so when you have an odd looking population that's not normal, we can't say anything about that based on this video. This video works under the assumption that your population starts out normal. We focus on that one scenario first, okay? So that is the big idea there. What is the shape of the sampling distribution of a sample mean when it's taken from a normally distributed population? Just like with P problems, we're going to say that it's approximately normal. Does the sample size matter? Not really. The 25 picture was tighter, and that's why it looked kind of funky on that same scale, but it does look approximately normal if we were able to zoom in better. So you get less variability when the sample size is bigger, but you get like a tighter normal curve than you do with a smaller sample size. Okay? Again, we're only in this video looking at when the population is normal. So on this next slide, we have an example problem that we're going to walk through here. So let's look at what's going on. We're looking at peanuts placed in jars, and the distribution of weights of jars, so how much the jars actually weigh, is approximately normal. The mean is supposed to be 16.1, and the standard deviation is 0.4. So when you have different jars of peanuts, they have an advertised weight on them. But obviously not every jar is going to be like down to the thousandth of a ounce the same. There's going to be a little bit of fluctuation there. But the actual distribution of jars is approximately normal. They tell us that in the problem. The mean and the standard deviation are given to us. So this first question here is a thinking question. Without doing any calculations, explain which outcome is more likely. Getting a single jar and finding, oh gosh, this single jar weighs less than 15.5. Or picking 10 jars, averaging them, and finding, oh gosh, my average is less than 15.5. So I need you guys to think about that. Pause me, take a little think time here, and tell me which of those two possibilities is less likely. Or does it say more likely? Let me see. More likely. Is it more likely that one jar is too light, way too light, or that the average of 10 jars is way too light? Kind of gave it away in my last little rephrasing of the question right there. It would be a lot more surprising if X bar, the 10 jars, is less than 15.5. So I keep tripping up the wording of the question. The wording of the question says which is more likely, and the more likely is a single jar. I'm going to talk about it, but I'm not going to actually write anything for this problem right here. A single jar defying the odds and being super light would not be like unheard of. You could have a fluky jar that you just happen to pick. But if you pick 10 jars, to get an average that low of 15.5, that would mean that all 10 of those jars, or at least a bunch of them, were way too low. It's more likely to find one weird jar than 10 weird jars. That's the basic idea right there. And I'll pause and write something up here just so you guys can have an answer for this question and you can see what's going on. But the idea I explained is basically what I'm looking for. All right, so there in blue, you have like a little written up explanation of what I just went over right there, but get something like that written down just to have a model to look at later. But one jar defying the odds is more likely than the average of 10 jars doing that same thing. X bar is less variable than your original data sets, just like in the money example from earlier. So we're going to find the probability for each of these two things happening. And as a reminder, the mean for this problem, the mean of all the jars was 16.1, and the standard deviation was 0.4, I think? Yeah, 0.4. As a general rule, don't write down variables in problems without defining them somewhere. So when I actually do my big problem, I'm going to define U. So don't use symbols without defining them in general, but I'm putting this just to save myself a little bit of effort here. So there are two things they're asking you to find. They're asking you to do it for a randomly selected jar, and then they're doing it for 10 jars. One jar is nothing new in this chapter. One jar is like a chapter 2 question from last semester. You can handle the first part, and I want you to. I'm not even going to go over that whole thing and write it out. I'm just going to slap the answer up there for you guys. So pause and try to do the first one yourself. The second one with the 10 jars, we're going to do together. Okay? All right, so I have the answer to the first question worked out right here. Again, if you're looking at one jar, you're not even doing this chapter stuff. You're just doing a normal CDF question. So I set my lower is 0 because you can't have a jar that's less than 0. If you did negative 10,000, that's fine too. Doesn't really matter. You just do upper is 15.5, blah, blah, blah. It's about 6.68%. So not super likely, not incredibly crazy rare either, like impossible, but there's about a 6 or 7% chance of getting a jar that is that light. Okay? Nothing new in that part of the problem. I'm going to go ahead and delete this, and then I'm going to show you guys how you set up the new problem. This second question is asking about the average of 10 jars. As soon as you see that you're taking a sample and you're looking at an average, now we're in chapter 7 territory. We want to know how likely a certain value for our sample mean is. That's exactly what this chapter does. So step 1 is even realize that you're in the right chapter right here. When do I do this chapter stuff? Well, it's when you take a sample and you look at how likely getting a certain result is. Because a sampling distribution is all the possibilities for that sample. So it's logical that we would use that to do a probability. So first thing, realize you're even in this chapter. Okay, fine, I'm in chapter 7. What happens now? You're going to define your variable. You're either going to define P if it's a P problem, or mu if it's a mu problem. And this totally is a mu problem here. We're looking at an average. You could also get by with defining X bar or P hat, but some of my old answer keys, I would do that. I ended up just always doing mu or P though, because it's easier for later chapters. So I always define the parameter nowadays. If you see me do a sample, like a statistic, that's okay, but it's just define one of them. So mu is going to be the true mean weight of a jar of peanuts. Okay, variable defined. Next thing I'm going to do is I'm going to look and see, well, okay, is the population, is my X bars graph going to be approximately normal? And for right now, we learned that that is true if the population is normal. If the population isn't normal, for right now, it's just, can't do anything. But because it's in this lesson here, it said, hey, the peanut jar population is approximately normal. So since the population of jars or jar weights is normal, the distribution, the sampling distribution of X bar is approximately normal. So basically, when you do a chapter 7 problem, you have to justify why can you do normal stuff. Eventually, the punchline of these problems is do normal CDF. That's what happens. But you have to set up the problem first and show that you're able to do that. For right now, why can you do normal stuff? Well, the population is normal, so X bar is normal as well. That's what you say. So we've established, okay, cool. We've got a sweet normal curve in these problems. So we know we can actually do normal CDF stuff, but what numbers do we use? Well, we need the mean and we need the standard deviation. So the mean for X bar's graph is just the mean for the population. And the mean for the population, it said earlier, was a 16.1. So that's cool. 16.1 is my mean. This is X bar's graph right here. The standard deviation, first of all, before I calculate it, I need to check that the sample is not too big, because I am sampling without replacements. We're picking 10 jars, and 10 is definitely less than 10% of all jars in the factory. Gotta check that 10% condition before you do standard deviation. So we're good there. Now we can do the standard deviation for X bar. And the formula for that, it is not the same standard deviation of 0.4 that we just used. We just did that problem a minute ago. Kids always forget to actually find the right standard deviation. What you're supposed to do is take your population standard deviation and divide it by the square root of your sample size. So what I would need to do is take that 0.4 and I would need to divide it by the square root of 10, which if I type that in my calculator, 0.4 divided by square root of 10, it's like 0.126. X bar, its graph, is less variable than your population. So you should have a smaller standard deviation. I wouldn't want to use that same 0.4. My new standard deviation is the smaller 0.126. And then we're asking for the same probability. We want to know, oh, how rare is 15.5? So I'm going to do another normal CDF, just like I did before. I'm going to do a normal CDF. My lower is still 0. My upper is still 15.5. My mu is still 16.1. The only thing that's different is that standard deviation. Now, before you type this in the calculator, as I'm getting it right here, you should ask yourself, will this answer be bigger or smaller than the other one? And if you type it in, it turns out that it is way smaller. It's like 9.6 e negative 7, it says. Never write 9.6. That's terrible if you do that. Remember that scientific notation. So basically, if I was going to make this decimal, e negative 7 means times 10 to the negative 7, that's 6 zeros. It's like this. Or you can just go, it's approximately 0 for our probability. Super, super low. Okay? Just like we talked about. 1 jar defying the odds and being super light, possible. 10 jars defying the odds and being super light, not so likely to happen. So this probability is much lower, much less possible than the single jar example. Now we've shown that with numbers. So the only thing I'm missing right here is just restating the probability of taking a sample of 10 jars and finding the average to be less than 15.5 is approximately 0. And you would just add that on and then that's good to go. Okay, so these problems are somewhat similar to last section with P. It's just different things you have to check before you're allowed to do your normal CDF. But it ends in a normal CDF. That's the punchline of this chapter. Check some stuff, and then you can do probabilities with normal CDF. Most common error by far in these problems is remember to divide by the square roots of n. I've looked at kids' tests. I've looked at AP tests. It's such a common error. The people writing the test know you're going to forget. So they put this on there and people mess it up all the time. It's an X bar problem. You're looking at the graph and they just grab the sigma from the population. They forget to divide it by square root of n. So don't make that mistake. You totally will. So prove me wrong and don't make it. It's really a big deal.